Good day, class. I hope you're having a pleasant time, regardless of the time of day you are watching this. Today we'll be going over Handout 12, in which we will be going over Section 3.7, related rates of change in the natural sciences. And then on the back half of this handout, we'll be going over Section 3.9, related rates. All right, so let's start our conversation with an example from physics, which is in large part the motivation behind much of the early development of calculus. And we begin with the example of a damped spring. And so a damped spring is simply a spring that has some kind of friction holding it back. And so we have this equation right here that we're going to be dealing with, and this is going to describe the motion of a spring. So imagine, if you will, you have a spring, and it's being pulled downward, and so you expect to see the spring, accordion down after the initial pull. It's going to be going right back up to here, and it'll be yo-yoing back and forth in between these two states. Okay. Now this term right here is going to be slowing it down. That's called the, this is the amplitude of the initial pull, but this E term right here, that's going to be our, what's caused our models are dampening. So let's take a look at this graph in Desmos. And we can see this graph right here. If you can see, this has a period of pi, as we would expect from right here. Again, the period is going to be 2 pi divided by this number right here in the front. And that does seem to be, in fact, what we have here. And note that the amplitude in the beginning is 10, but then the amplitude becomes less and less as time goes on. And once again, this y-axis is the distance of the spring from its resting point, and the x-axis is going to be time. And so we note that this spring goes all the way up and all the way down to these two dashed blue lines, which are this line here and this line here, and note that these terms correlate to that term right there. And so it's squeezed in between those two terms, if you will, if you remember that term from earlier in the semester. So now let's get to following the next set of directions for this problem. We want to find the velocity function. So let's go ahead and restate our original equation here. All right, here's our equation, and now we want to find the velocity equation, and remember that the velocity equation is just the derivative of the position equation. And to find the derivative, we are simply going to be using the product rule for derivatives, and so we've got this function here followed by this function right here. And we got a little constant hanging out in the front, so let's just go ahead and factor that out in the beginning. And so now let's go ahead and take the derivative of the yellow part, and when we do that, we get like so. And then we must find our next derivative of the blue part right there, and that is simply going to be -2 times sine of 2t, since the derivative of cosine is negative sine, and we are applying the chain rule. The derivative of the inside function is simply 2. Okay, so we can clean this up. We can factor out our e in both sides here. When we do that, we get a much simpler expression, which is got the negative sign right there. Make sure you include that to get this expression here nice and clean. So that is our velocity equation right there. Okay, so let's take a look at this in Desmos. Alright, so we have this set up, and let's go ahead and take a look at it now. This equation here in blue, that is our velocity equation. Let's go ahead and zoom in so we can get a better idea of what's going on here. Alright, so I zoomed in on one of the portions of the graph, so it's a little less busy here. And what you notice is, again, first off, the red is the position away from the equilibrium of the spring, right, the y position. And then for this purple graph, the y is the velocity at time t. And I want us to notice a few things. When our spring is at a maximum distance away, like it is right here, note that the velocity is 0. Again, right here, note when it's a maximum distance away on the other side, again, the velocity is 0. So anytime you get a maximum distance away, when you're turning around to come back, your velocity is 0 for the spring. Also note that when you are at the equilibrium point right there, when the spring passes through the neutral position, you are at a maximum velocity up here. And again, look right here. Right here, you're in a neutral position right here at 16.5, and you're at a maximum velocity on the other side. So you see this interplay between the position of the spring and its velocity. Alright, so we've done all the directions listed here. Note we could take another derivative of the velocity and get the acceleration function of the spring, and then take another derivative, and then that would be the jerk equation of the spring, and we could keep on taking more and more derivatives. In fact, there is no limit to the number of derivatives we could take, since this right here will always generate more derivatives, and the same is true for both trig functions. Unlike, say, x to the third, where if you take 3 derivatives, well, you can't go beyond that. Alright, so let's change gears here and take a look at some economic functions. And so here, under economics, one of the big things that we're worried about is the cost of goods sold. And so we have the cost function right here. And again, this is just a function that is of x, where x is the units produced. Sometimes it's defined as units sold. And then we have the marginal cost. And the marginal cost is the cost to produce one more unit. And that is, if you've already produced X number of units, how much does it cost to produce that X plus 1 unit? And so the marginal cost is basically the derivative of the cost function. So this is one way in which derivatives are used in economics. Alright, so for some biology examples, this is be very quick and rudimentary. Let N be the number of microbes in your population. It doesn't have to be microbes, it could just be anything that you're studying. And so we have an average growth rate, which will be given by the average change in the number of organisms that we're dealing with per time. Change in organisms per time. Right, and so again, this is just N2 minus N1 over T2 minus T1. Now, oftentimes we want to get this as a function, and so we're going to come up with an instantaneous growth rate. Because that'll tell us how it's behaving when the time stamp is incredibly small. And so this is simply the limit as delta t approaches 0, the change in time, of delta n over delta t. And that gives us our derivative function right there. Next, we're going to look at laminar flow in a blood vessel. And basically, for laminar flow in a blood vessel, we just treat this as if it were the same, mathematically speaking, as it were for any kind of fluid flowing through a pipe. So you've got this guy here, you've got stuff flowing in, which, you know, if it's a blood vessel, you know, be blood, hopefully. And so when you look at this, at any kind of cross section here, the velocity profile is going to be the most in the middle and the least on the sides. And the greater this gradient is along here, the more pressure you're going to be giving on the blood vessels, which is what causes a series of health conditions if this velocity gradient ever gets too much, causing friction on the artery walls. And so we also need to make one more point. You know, we measure from the central point on out, and that is little r. Little r is how far you are, any point is away from the center of the vessel, and then big R is the total distance. So little r is a variable, big R is a fixed constant. And so one way, the way we find how much friction is acting against the artery walls is we have to find the velocity gradient of this velocity profile here. And with that's just a fancy way of saying the change in velocity per change in position. And so we just take the derivative of this guy right here. Now it's important to note that, you know, P is going to be a constant in this particular section of a blood vessel. This is a viscosity constant. This is the length that's not changing. And then again, of course, big R is always a constant, so your only variable is this little r right here. So when we take the derivative, we simply abide by the derivative rules. These guys all stay the same since they're being multiplied. And then big R right here, well, derivative of a constant by itself is 0. And then we take the derivative of the next guy, negative 2r. Clean that up, and we get this expression here. Note that this 2 and 4, you know, the 2 will cancel, leaving us with a lower, just a 2 down there, resulting in negative rp over 2 and L. All right, so that's our survey into some of the sciences. You know, we just very briefly scratched the surface. Of course, we can go much deeper into these subjects using calculus, but just trying to get you an introduction at this point. So let's move on to section 3.9, related rates. So on this question here, we have an oil spill. And this oil spill, the radius of this oil spill is increasing by 0.26 meters per second. That's the equivalent of 30,000 barrels per day. And so we want to know how quickly is the area increasing. We know how quickly the radius is increasing, but we need to know how quickly the area is increasing. And so first thing we need to do is we need to spout out the equation that relates radius and area together. And of course, that equation is area equals pi r squared. Okay, now this is going to be very similar to implicit differentiation, but there's going to be a few key differences. Area is a function of time. The radius is also a function of time. You don't need to remember f and g. What you need to remember is that area and radius are both functions of time. And that when we're going to take the derivative of both sides because we want to know how quickly the area is increasing. We are not taking the derivative with respect to x. We are taking the derivative with respect to time. So let's go ahead and write that out. So we have our derivatives with respect to time, and then we just stick everything in, our area and pi r squared. Now, when I write a prime in a second, I want it to be very clear that when I say a prime, I mean the derivative of the area with respect to time, and when I say r prime, I mean the derivative of the radius with respect to time. Note they are both going to be with respect to time. Okay, so over here we have a prime, and then on the right hand side we take the derivative. So we have 2 pi r, right? Because the derivative of r squared is 2r. Don't forget the r prime. Okay. And then let's go ahead and plug in what we know. R prime is 0.26 meters per second. Plugging that in, we get a prime equals 0.52 pi times r. And so now we know how quickly the area is spreading for any given radius. And so if I asked you, okay, well, how quickly is this guy spreading when the radius equals 1? Well, that is simply plug the radius of 1 into there, and that would be 1 meter, of course. Then a prime would simply be 0.52 times pi, which of course is there it goes, 1.63, and that would be meters per second, as a per example. Okay, so let's go ahead and look at the next example. Also a circle of sorts. The last one was a two-dimensional circle. This one is a three-dimensional circle, a sphere. And so we've got a water balloon, much more benign example, that is being filled up in the shape of a sphere. And we know that water is flowing in it at a rate of 10 cubic centimeters per second. And so we want to know, how is the radius changing with time? So once again, we got to relate two different quantities with an equation that we already know, and we want to relate volume with radius. And so the volume of a sphere simply is 4/3 pi r cubed. And now we're going to take the derivative of both sides, keeping in mind that the volume is a function of time and that the radius is also a function of time. And we will be taking the derivative with respect to time, not with respect to the radius. Okay. And so let's go ahead and just make this very clear by writing this as follows. Like so. And then let's plop everything in here. 4/3 pi r cubed. Okay, so you take the derivative of the left side and we get v prime. Again, v prime means the derivative of the volume with respect to time. Okay? And then we come over here, we have 4/3 pi, since that's, constant times a variable, and take the derivative of r cubed, which is simply 3r squared multiplied by r prime, where again r prime is the derivative of the radius with respect to time. Okay? And so we know right off the bat that the 3's cancel. That's pretty nice. And so let's go ahead and restate this. The rate of change of the volume equals 4 pi r squared multiplied by r prime. And what is r prime? Well, we're not given r prime, but we are given the rate of change of the volume, which is 10 cubic centimeters per second. And so we plug that in. 10 equals 4 pi r squared times r prime. And again, we're looking for how the radius is changing, so we need to solve for r prime. And so we write r prime here, divide everything in the front. And so we get r prime equals 10 divided by 4 pi r squared, which can reduce to 5/2 pi r squared. And that's it. That is how our radius is changing for any given radius at any point in time. Okay, so now on to the final example down here. We have a 20-foot ladder sliding down a wall. This is a very famous problem. It will likely be on the final, so you want to pay attention to this one. We want to know how quickly is this ladder falling if the bottom part of the ladder is moving away from the wall at 2 feet per second. So let's get the setup for this down. So we have this ladder here in green propped up against the wall, and the bottom of this ladder is moving away from the wall at a rate of 2 feet per second. And so note that because the way the wall is set up, we can pretty easily impose an x and y coordinate system onto it. And note that as what we don't know is how quickly is this guy falling down. We don't know how quickly it's going to slam down into the ground. And let's call this quantity v. And so the other thing that we know is that this ladder is 20 feet long. So we want to relate the x and the y to this guy right here. How do we do that? Well, Pythagorean's theorem. X squared plus y squared equals 20 squared. Which of course is 400. So here we're going to take the derivative of this equation, not with respect to x. Note that note what x and y represent here. X represents this coordinate right here, right? And that coordinate is changing. That coordinate is moving to the right. And what does y represent? Y represents this coordinate right here, and that coordinate is changing. It's moving down. So both x and y are changing with time. X and y are variables of time. And so we're going to take the derivative of this equation with respect to, you guessed it, time. And so when we do that, we get 2x times x prime, where x prime equals the derivative of x with respect to time. And so plus 2y times y prime. And then on the right-hand side, of course, the derivative of a constant is simply 0. Okay, so note that we can divide through by 2. Get rid of those 2's. That makes things a little bit easier. Also note that x prime is how quickly the ladder is moving away from the ladder. We already have that right here. That's going to be 2. And also note, what is y prime? Well, y prime is our v that's moving downward. So let's go ahead and plug these numbers in. And when we do that, we get x times 2 plus y times v. Okay. And of course, that all equals 0. And again, we're trying to find what the velocity is doing. So we're going to solve this for v. And when we do that, we get v equals negative 2x times y. Now we want to get this strictly as a function of how far the ladder is away from the wall. And so to do that, we've got to come back to this equation right here, and we have to solve for y in order to get rid of this y right here. So we're going to come off to the side here. Alright, so we're going to come right over here, and we're going to solve it for y. And we have y equals the square root of 400 minus x squared. Note, I'm not taking a positive or negative right there, as a negative sign in front would make no sense, because a negative sign would imply that the ladder has a position down here underneath the floor. So we're not taking those, we're only taking positive values over here. Alright, so we're going to take this, we're going to plug it in to right there. And when we do this, we get the following result: negative 2x divided by the square root of 400 minus x squared. And there we go. There's our final result. Now I encourage you to plug this result into Desmos just to kind of get a feel for the graph, and do the same for the previous 2 examples that we did. Just graphing just kind of helps you get more of an intuitive understanding for what these equations are telling us. So that's it. That's the handout, and I will talk to you guys next time.